I'd go fast food.
All right, well, it is time to begin again. Today is, let's see, July 29th already. We're rapidly coming in on the end of the semester and the end of the summer. It feels like summer has just finally gotten here weather-wise, and calendar-wise it's almost done. So it seems like if things keep continuing like this, we won't be skiing until like February, and then or something like that. I don't know. Either that or it'll be one of the shortest summers on record, and we're all going to be ready to fly off to Florida come January or something like that. But so let's see. There's a possibility that we may have to push the exam off one day to Tuesday. But we'll look at that and see. There's a project sponsor coming into town, and he may require, or I may need to be there for that on next Monday night. But I haven't heard for sure if that's when he's going to be around. But if that's going to be the case, we may have to push the exam off one day to Tuesday. But we should be able to hear about that within the next day or two. So for those of you who have to take off work or something, we'll give you plenty of advance notice. And that exam, I think, for the sake of getting things done for the off-campus students, we will probably kind of cut the material off at the end of this lecture 7 stuff, assuming that we get through it. But yeah, so there should be a little bit of the more advanced Thevenin problems, the first and second order transient problems, and then some basic AC analysis problems that will probably give us a good idea of what the exam will look like. But homework on the chapter 7 material, I think it is due tomorrow at the beginning of the class. I've got one question that someone had that I'll take a look at real quick at least. And then we'll take a look at any other questions if you've got them. Otherwise, we'll go back into AC analysis. So the question that we're looking at is number 779. And the idea here is that it's rather than just explicitly saying, hey, your initial conditions are X and Y, it makes you solve for them instead, doing just a mild amount of circuit analysis and remembering that, what is the steady state behavior of a capacitor or an inductor. So in this case, the key thing that you need to solve for, at least first, well, what are the two initial conditions that we need to know for second order parallel circuits like this? We need to know the voltage across the capacitor at time 0, and we need to know the current through the capacitor at time 0. And so those are the two key things that you need to do just a tiny amount of circuit analysis for. So what is the voltage across there? Well, let's write a KVL equation around and find out what's going on. So we have negative 12 plus whatever the volt is across that 2 ohm resistor, the voltage, plus the voltage across the capacitor, and that equals 0. So solve that for the voltage across the capacitor, and you get it's 12 minus whatever the voltage is across the 2 ohm resistor. But what is the behavior of a capacitor at steady state? It acts as an open circuit. So that means that no current is flowing through the circuit. And what is the voltage across the resistor if there's no current flowing through it? 0. So the initial voltage across the capacitor is simply equal to 12 volts. But we've already also kind of figured out what's going on in terms of what's the current running through the capacitor. Well, there isn't any. So just a mild amount of circuit analysis to figure out what the initial conditions are. Then when the switch actuates and goes from one point to the other point, what you're left with is just the standard parallel RLC circuit that we've been looking at before. 10 ohms. And it wants you to find what is the voltage across these elements with respect to time. And after that, solve for alpha, solve for omega naught, using the standard procedures. So that's what, 1 over 2 RC and 1 over the square root of LC. Plug in those numbers, figure out the appropriate damping, solve for the appropriate constants. You've got your initial conditions, so run with it from there. And that's the wrinkle is just to do a little bit of circuit analysis to figure out what are the initial conditions. Any other questions specifically on the homework? Well, if you do have questions, I should be in my office most of the day today. I don't have anything specific that should take me out of the office, so I will just be in there trying to do some preparation for various things. So if you do have a question, just let me know. That's what I'm here for. So, all right, PowerPoint slides, AC analysis. Let's go over the things that we talked about yesterday. So what we're going to talk about during Chapter 8, again, is we looked at sinusoids and phasors just a little bit to get that back into your memory. We looked at, and we're going to start looking today at phasor relationships for circuit analysis or for circuit elements. We'll examine these concepts of impedance and admittance. We'll look at phasor diagrams, which are entirely useless to me personally, but they might give you some additional understanding, I don't know. And then we will start applying pretty much all of our circuit analysis techniques from the previous chapters, everything except for first and second order transient analysis, and analyze some AC circuits. And we'll find very quickly that the math gets nasty, and it gets harder for me to give you exact answers. And so as long as yours is pretty close to whatever I get, life is good. So we looked at the general form of a sinusoid. It has some sort of magnitude, it's some sort of frequency, and potentially has some sort of phase angle associated with it. Frequently, well, if you get a frequency that's given to you in terms of hertz, we like to express that in our sinusoidal functions as a radian frequency instead, and so you multiply that, I guess, linear frequency, whatever, the frequency in hertz, by 2 pi, and that will give you the radian frequency. So that's our final form for most of our sinusoidal functions will be some magnitude times a sine or a cosine. We kind of prefer cosines for whatever reason, but cosine of omega t plus theta, where again omega is the radian frequency and theta is the phase angle of the sinusoid. We talked about the difference between when you have two different sinusoids and they have different phase angles. The one that's a little bit farther left in the or that crosses the origin farther to the left or crosses the x-axis farther left on your diagram, that one leads the other one by the difference of the phase angles. And then you can look at that just from the other way and say, okay, well, the second one lags the first one by that same difference between the phase angles. And for whatever reason, a bizarre convention, while we prefer to express the radian frequency as in radians, we always, for some reason, express the the phase angles in degrees instead of radians. Just, I don't know, maybe to confuse you. Identities that, for the most part, we will never use, but in the event, there are some problems here and there that ask you to deal with a sine instead of a cosine, and you just make that conversion by adding 90 degrees to get yourself to the cosine. Or I guess subtracting 90 degrees to get to the, if it's specified as a cosine, you subtract the 90 degrees or the pi over 2 radians. The way that we use phasors in this class at least is maybe a little different than the way that you did in DSP, because we use the angle notation instead of the e to the j theta notation. So if you're given some sort of sinusoidal function in terms of these, either this voltage or this current, we have some sort of magnitude, we have some sort of frequency, and we have some sort of phase angle. When we express that as a phasor, we just take that magnitude, we take the phase angle, and we stick the little angle sign in between it. One of the typographic conventions that we'll do as much as possible is to make this, all of the vectors or the phasor should be a boldface font, but it's kind of hard to make that happen all the time. So one of the things that I will tend to do, and I don't know if this will show up real well, but is to kind of do a double slash or something like that. That just looks like scribbles. Anyways, I'll try to do some sort of double slash or otherwise indicate that it is a phasor, because you should try to do that. And unfortunately, we don't have the same kind of idea as, okay, here's a vector or something like that. We don't have that kind of notation. But one of the things that is very key that you should notice about the phasors is that there's no frequency information there whatsoever. And so you have to be careful when you're messing around with phasors that there isn't some frequency-specific information that you're somehow losing out on or forgetting about or otherwise ignoring. But normally you can, that's okay, because everything within a circuit should be operating at the same frequency. So, right. So we did at least a couple of quick examples. I did the first V1 of T and the phasor V1. So we can take a look at the other two just real quickly so that you're hopefully feeling comfortable with this. And get out the cheater notes here. And, all right, so we've got another phasor, or another time function V2, which is given as 18 times the sine of 2513t plus 4.2 degrees volts. And we want to know what is the phasor value V2. The key thing to note here is that this is a sine function and not a cosine function. And so to kind of transform it into a cosine function, we'll subtract 90 degrees from the phase angle. And so this could be expressed as 18 times the cosine of 2513t minus 85.8 degrees volts, which just makes the phasor 18 at an angle of negative 85.8 degrees. So then we're also given another phasor V2, slightly different guy, where it is 12 at an angle of negative 60 degrees. And that was odd. I wonder if we've, if some of the campus lost power or something.
I think we're still going.
It seems to be okay. I'm still seeing lots of things on the screen, and so, hey, that's our excitement for the morning, because circuit sure ain't going to do it. All right, so again, if you just have this, you don't have frequency information, and so you can't turn it into can't directly turn it into a phasor unless you have that frequency information. And the slide indicates that the frequency, again, is going to be 400 hertz. So if we want to, we could multiply that out. Yesterday I kind of cheated and said, well, it's 400 pi, but 400 times pi is 1256-ish. So we can say that it's 12 cosine of, about 1256 t minus 60 degrees volts. And that's the time function, V2. So it's fairly straightforward, and you know, it's the kind of thing that it's almost kind of hard to screw up. Just kind of grab the information, pay attention to frequency information as it's necessary, but it's generally not going to be, at least for voltage sources and current sources, it's not going to be a really big deal. Now what we will see is that that frequency does matter for certain other circuit elements, not resistors, but it definitely matters for inductors and capacitors. The frequency that we're operating at is has a big impact on, yeah?
Isn't it 2 pi? Would it be 800 pi?
Yeah. Yeah, so what it's doing, 2513. Thanks. So the frequency doesn't matter a ton to the behavior of the current source or voltage source, and it also doesn't actually matter a ton for resistors either, but it does affect the behavior of inductors and capacitors in AC circuits. So let's take a look at the relationships for those things so that we can formalize all of those. So we already established that for a given resistor, that the voltage across it equals the resistance times the current that's going through it. And if that's the case, that the voltage as a function of time equals the resistance times the current as a function of time. And you know, in the past when we were looking at this, you know, these were constant functions, and so we could kind of safely drop the time aspect of it and just say V equals IR. But when we turn those into phasors, we can also say V equals R times I. So what that means practically speaking is that there's no complex part or no complex response on the part of a resistor. Regardless of what the frequency is, the voltage and the current will always be in phase. And so if you look at that from the point of view of a phasor diagram, if we have some sort of voltage and some sort of current, and these are both vectors, this would be the phasor diagram. Everything here is the real axis, this is the imaginary axis, and those things should be in phase, and they will, yeah, and there won't be any kind of difference between them. If we visualize that as a sine instead, we could have it doing whatever that happens to be, and the current would just be, so the voltage is on top and the current is on the bottom. And so they're in phase with each other, they have different magnitudes, but everything just kind of works nicely and in phase. There's no complex portion to the response. So that's kind of the key thing. So just in the way of a trivial example, but hopefully something that makes this clear, because I'm getting a few kind of confused looks. If we know that the current through a resistor, there's a 4 ohm resistor, and the phasor current we know going through it at 12 and an angle of 60 degrees, and that's in amps. What is the voltage across that resistor? Wow, that just looks like, I have no idea what that's supposed to be. Yeah. So what is that voltage? Well, we just in this case, what you could, I mean, you can plug this into your calculator and you can go to it. Say, well, all right, well, 12 at an angle of 60 degrees times 4 ohms gives me, let's make that useful, gives me 48 at an angle of 60 degrees, and that's what we kind of expect to see, right? Because what I just told you is that the current and the voltage are in phase for a resistor. And so the phase angle for the current and the voltage are both the same, and it's just a difference. What is the magnitude? Is it the magnitude of the current was 12, the magnitude of the voltage was 48. So there's nothing particularly odd there or something. What we want to do, though, according to the slide, is to take a look at what is the voltage as a function of time if the frequency equals 4 kilohertz. So 2 pi f to give us the radian frequency. Again, we can kind of cheat and say it's 8,000 pi, but that's also 132.7, whatever. And so the voltage across the resistor as a function of time is 48 times the cosine of 132.7 times t plus 60 degrees volts.
Multiply it over, we just keep pi in there.
You can do whatever you feel comfortable with. You can leave it as 8,000 times pi or whatever. One of the things that we will very quickly see is that calculators will deal with these complex numbers differently. Depending on exactly how many significant digits you try to keep around, that will change the answer very, very slightly. So, you could give me this and say, well, it was 48 cosine of 8,000 pi, or 48 cosine of 25/132, or 132.74, or whatever. So, whatever kind of makes you feel comfortable. I don't care. So that's the relationship for resistors. The response is in phase. There's no complex portion to the response of a resistor. There is, however, a complex response for an inductor. The phasor voltage across an inductor is given as J omega L times I. So that's the voltage current relationship. You have a voltage, whatever that is, and it's multiplied by this J omega L quantity. So there are two important things that come out of that. The first is that the frequency, I guess the voltage current relationship is frequency dependent. If at higher frequencies for the same current, same magnitude current, the voltage is going to get a bunch larger without changing anything else. The other thing is that we do have the complex response. There is that J term as part of the response between these two things, and so what that means is that voltage and current will be 90 degrees out of phase. And in this case, the voltage leads the current. So visualizing that for those of you who do happen to be more visual type learners, again, if this is the imaginary axis, this is the real axis. We can have I coming out at some magnitude, and we'll have V coming out at some 90-degree difference. And that's the voltage. In terms of like a sine wave kind of thing, we would have, let's try to put top up here and down here. So that might be the voltage waveform. And then the current is going to be 90 degrees out of phase with that. So something like that. And so that's voltage, that's current. And the voltage is leading by 90 degrees. There is one kind of interesting thing here, and this is more of an aside than anything else. What is the frequency of DC current? 0. So the voltage across an inductor is J times 0 times L times I. An inductor acts as a short circuit under DC conditions. It's just another way to express the behavior there. Yeah?
Those two are not the same magnitude, right? They're different.
They might be. I guess if your inductor was L, or if your inductor was 1 Henry, they might be the same magnitude. But the one that's further left along the axis is the one that's leading. So it is a little backwards, I think. I think intuitively, I want leading to be farther to the right, but unless they've changed the figure it's opposite. I guess they changed their minds because the version that I have has the voltage on the left and the current on the right. That's weird. I don't know. It's one of the reasons that I don't like these diagrams anyways. I kind of like to just work with the numbers. But I'll take a look at that and try to get that cleared up. Oh, you're looking at the capacitor one? Okay, good. So that's an inductor. So we can do the same kind of very simple analysis with an inductor. So let's say we know that the phasor current in the inductor happens to be 4 at an angle of negative 30 degrees amps. The value of the inductor itself is 0.05 henries, and the frequency is 60 hertz. And again, that means that without doing any math per se, and just kind of making an equation in your head, 60 hertz means a radian frequency of 377 radians per second. So the relationship that we have is it says that the phasor voltage equals J omega L times I. So start plugging stuff in. We've got J, we've got 377, we've got L, which is 0.05, and we've got the phasor current, which is 4 at an angle of negative 30 degrees. So you should more or less be able to plug all of that into your calculator. Say, all right, we've got J times 377 times 0.05 times 4 at an angle of negative 30. And yes, what that should give you is a value of about 75.4 at an angle of 60 degrees. And what is, I think, hopefully fairly straightforward is that we can multiplying this J by the phasor part would change that would make it 60 degrees instead of the negative 30 degrees, and then you can just multiply all of the magnitudes together. 377 times 0.05 times 4, and that should give you 75.4. Again, like I mentioned yesterday, we have a tendency to express, it's very odd that we express like this chunk in a rectangular form, and we express that current as a phasor. And I don't know what the convention is there necessarily, but that's what we do. I'm not sure why, but. Any questions on how we get that number? So hopefully as you're poking away at your calculators, you're seeing where these numbers are coming from. You're getting the same kinds of numbers, and if you're not, please let me know at some point so that we can verify that you're going to be able to do the work on the questions as well. We've got one for capacitors too, a phasor relationship. For this one, we switch things around just a little bit. And you'll see that it used to be a voltage times the current times some mess of stuff, and now it's a current equals a mess of stuff times the voltage. And so obviously we could rewrite this to get it in the same kind of form and say that the voltage equals the current divided by j omega c. But for, whatever it's worth. So again, there's two things to pay attention to again. Here, and then this obviously can be, whenever you see a j in the denominator, you can pull it up onto the top and make it a negative j. So this is, we can say negative j for omega c times I gives us our voltage. Try to make that look more like an I. So that's our voltage, is this negative j over omega c thing. Again, the two kind of takeaway messages are, because there's an omega term in it, it is frequency dependent, and so, but it's inversely frequency dependent here. The larger the frequency, the smaller the voltage will actually get, because this denominator gets larger and larger. And then because we have the negative j here, they're going to be 90 degrees out of phase again, but in this time the current leads the voltage. So our takeaway message is the omega term means it's frequency dependent again. And the negative j term means 90 degrees out of phase, current leading. So our ever so useful diagrams, which I still really don't like, if we had a voltage that was coming out this way, the current would be 90 degrees out of phase this way. Wow. The magnitudes will obviously depend on the frequency, and then if we look at the sine waves, they may or may not be the same magnitude, but you'd have the current leading the voltage by 90 degrees. So this one's the current, and this one's the voltage. So and we can do another quick example of the same kind of thing. So we have a known current in a capacitor that is 3.6 at an angle of negative 145 degrees. The capacitance is 150 microfarads, and the frequency is 60 hertz. So the radian frequency, again, we can just jump right in and say it's 377. And our relationship that we have is I equals j omega c v. So we can start kind of plugging stuff in. We've got 3.6 at an angle of negative 145 equals j times omega times 150 microfarads equal, or times the voltage. So if we want to know what the voltage actually is, it will equal the 3.6, an angle of negative 145, divided by j omega 150 microfarads. So, and again, omega was 377, so we can take and divide 3.6, angle of negative 145, divide that by 150 e negative 6 times 377, and put that in polar form. Whoops. And you should get 63.66-ish at an angle of negative 235 degrees. It shouldn't, but when I just plugged this into my calculator, what I typed in was 3.6 angle negative 145 divided by 0 comma, let's see, what is 150 e negative 6 times 377 times 0.05655. And so it gives me a nice kind of straightforward form of doing that. And I guess if you have one of the pretty print calculators, it would be something like 3.6, 145 divided by I times 0.05655. And you should be able to get the same answer. Yeah. So, that is the relationship for a capacitor. Nothing too weird, I don't think. So, all of that kind of leads, I think, fairly naturally into the next idea here, which is this concept of impedance and admittance. Impedance is the one that I will care about the most. Admittance is the AC analog to conductance, and I've not found conductance to be of any use to me in all of the times that I've been teaching this class and taking the class as well. But impedance will become something that's very useful to you. And what we do find here is that impedance to some extent is the great equalizer, and now instead of just expressing things in terms of resistances, we'll express them in terms of impedances as well, or impedances. And now we can kind of, in a lot of ways, treat an inductor or a capacitor almost like a resistor, and we can start combining those things and finding equivalent impedances that take away some of the complexity of the circuit. Inductors and capacitors do have impedances. Impedances are complex values, and that comes about as a direct result of thinking about, Ohm's law says that the voltage equals the current times the impedance. It just so happens that in DC circuits, the impedance is wholly real and wholly resistance. There's no other complex portion to it. But because in AC analysis, V and I have the potential of being a complex number, the impedance itself also has a tendency, or also has to be complex by virtue of the math involved, I suppose. But like I said, instead of expressing its convention to express the impedance in rectangular form as that A plus JB kind of form, as opposed to the phasor form. Why? I don't know. To some extent, it does allow us to separate out the real or the resistive part of the impedance and the imaginary or reactive component of the impedance. I suppose that's a bit of a benefit, as opposed to having it kind of mixed and muxed together with the in the phasor version. But when you are looking to calculate the impedance for a given element within a circuit, what it kind of boils down to, if you can't read the stuff on the screen, is that for a resistor, the equivalent impedance is just the resistance. There's no frequency component to it or anything like that. For an inductor, the impedance, and this is a complex quantity, so it should get its double slash or whatever, that equals J omega L. And for a capacitor, it is, and the way that I learned this was negative J upon omega C. That was just kind of how but it's the same thing as I was just saying as 1 over J omega C. But the way that I remember hearing it the first time and the way that it sticks in my brain is negative J upon omega C.
And over there, then, it's just omega L?
Because that's just looking at the magnitude of the imaginary component. So those are the impedances, and so once you calculate an impedance for one of the elements, you can calculate it for all of the elements, and it gets, it does incorporate all of the frequency aspects. There is no frequency aspect to the resistance, but it takes into account the frequency things, and then you can start combining things, and all of these impedances take on all of the characteristics of resistors. So if you have parallel resistances, those combine reciprocally. Well, parallel impedances also combine reciprocally. Series impedances combine just additively. Same thing with the resistors. It's everything that you learned about combining resistors is fair game for combining impedances as well. And that's what's on the next slide is just, when you have a bunch of resistors or impedances in series, regardless of what kind of element actually gives you that impedance, you just add the suckers up, and that gets you the equivalent impedance in series. You add them reciprocally, and that will get you the equivalent impedance for a parallel combination. So let's try to do something with one of these impedances. And so here is our first real AC circuit. And this circuit, perhaps even yesterday, might have looked kind of scary. It's like, oh man, this is going to be a second order transient analysis or some other nastiness. And it's a series circuit, and we'd have to calculate, what is the damping frequency or the radiant frequency, and then have to calculate alpha, the Neper frequency, and all this other mess. But because this is going to be an AC circuit with a frequency of 60 hertz, we can turn this into something that's a whole lot more straightforward. So the first thing that we want to do is calculate just what are the impedances for each one of these circuit elements. The impedance for the resistor is just the impedance itself. It's 25 ohms. That's one thing that I neglected to mention on the previous slide is impedance is measured in ohms. Ohms is defined as the ratio of a voltage to a current or a voltage over a current, and that's how we calculate impedance as well. And so all of these impedances are given in terms of ohms. The impedance for the inductor is j omega L. It's 60 hertz, so that's going to be j times 377 times 20 millihenries. And we plug that in, we have 377 times 20 to the negative third. So that gives us 7.54. So it's J 7.54 ohms. And the capacitor is negative J upon omega C. So it's negative J over 377 times 50 microfarads. 377 times 50, negative 6. Flip that. So we get, negative J 53.05 ohms. Now here, as we were doing the dependent circuit analysis, or not the dependent analysis, but the Thevenin analysis on circuits that contain dependent sources, we always had to sit down and make sure that as we calculated the open circuit voltage and the short circuit current, and we took their ratio, that we better end up with a positive number, because this concept of a negative resistance doesn't really have any meaning. But not only is it meaningful for a capacitor to have a negative impedance, or this negative J impedance, it's pretty much required. I mean, that's what's going to happen. So it is not at all strange, it is not at all problematic to see something like negative J 53.05 as the impedance for a capacitor. And you should get used to seeing negative impedances, or at least negative J impedances. So, because all of those things are in series, the overall equivalent impedance is just the sum of those things, 25 plus J 7.54 minus J 53.05. So, really the only thing that you need to worry about here is summing up the two complex portions. So if you have 7.54 and you subtract 53.05, you get negative 45.51. 45.51 ohms. And that's the equivalent impedance. Now what we tend to do when we're once we have an equivalent impedance is we could replace all of those elements in the circuit, and we just tend to use a little box and say that box has an impedance of 25 minus J 45.51 ohms. And there's some voltage over here. Now, it's important to note that these numbers only hold for this particular frequency. If you change the frequency that the circuit is operating at, now the impedances for these, for the inductor and the capacitor change, and so you have to be aware of that and don't try to reuse all of that work. Yeah, question?
55.
5 what?
55 minus 45.51 J. Okay. You add them up together.
You got just 5? 55? I can double check, but if we have 25 entirely real plus 7.54 plus negative 53.05. Yeah, you should get 25 minus J 45.51. So the last thing that we would like to do with this is to just do a tiny bit of circuit analysis. If we're given a voltage, what is the current that's running around through the circuit? Just to exercise this a little bit. So let's see if we can. So let's say that source voltage, and I've been calling it V sub S of t, equals 50 cosine omega t plus 30 degrees. So the phasor current, or the phasor voltage, just equals 50 at an angle of 30 degrees. And we are told by Ohm's law that V equals I times Z. So if we want to, we can find out what the current actually is by dividing the voltage by the impedance. And here's where the numbers will very quickly get very nasty. So we say, well, 50 at an angle of 30 divided by 25 and negative 45.51. And put that as a phasor, and you get the eminently lovely value of 0.96-ish at an angle of about 91.21-ish. I guess 22 is a better number. Degrees. Amps. And like I mentioned before, this is not chemistry class. I don't care about significant figures, and so you don't have to worry about getting exactly the same number that I got. So we can turn that back into a time function just for kicks. 0.96 times the cosine of 377 omega t plus 91.22 degrees amps. Yeah?
When doing the original calculation of Z, when you're adding everything up, is it permissible just to add everything up and keep the 20, put 25 into basic form too, and add it all as one basic?
Yeah, you can think about it that way, I suppose. Create a wholly real and a wholly reactive impedance. If that makes you feel good, sure. Sure. That's fine. I think in terms of just making sure you guys have enough time for the quiz, we'll go ahead and call it quits here. What we should be able to get done tomorrow is to start looking at some more honest-to-goodness circuits. We've got some good AC analysis stuff to do. And if you have any questions about any of this stuff, let me know. If you have questions on the homework, let me know. Otherwise, we'll do this quiz. We'll see you on Wednesday. Have a good one.